Hello everyone, welcome to Verisec Toolbox channel. Today I will be showing you how to design a two-stage op-amp and do the corresponding analysis using TSMC65nm technology. This video is basically a front-end analysis. I will be showing you back-end analysis in the upcoming videos. So let's start designing the op-amp. So this is the basic two-stage op-amp circuit, and I have chosen some design parameters or design specification, you can say, according to which I am going to design the op-amp. And these are the constant parameters, that is mu p cox, mu and cox values of TSMC65nm technology. You can use these values in your design. And these are the BTH values, threshold voltage for PMOS and NMOS, it is 0.52 volt. And I have marked this MOSFET particularly so to make you better understood that this M1 M2 can be found out using GBW specification. Using slew rate specification, we can design our required bias current. Using ICMR minimum, we can use it and design the size of M5, and using ICMR positive, that is maximum, we can use to design the size of M3 and M4. And using the relationship BSG4 is equal to BSG6 from this circuit, and GM6, we can design the size of M6, and using the same current flow, we can design the size of M7. And using using phase margin concept, we can find phase margin specification, we can find the values of CC, and the relationship that are shown is 0.22 CL. CC is equal to 0.22 CL is derived from the Alan Hallberg book, and you can follow this book to know the relationship, how it is coming, what 60-degree phase margin. So let's start designing one by one MOSFETs size. So first of all, we will design M1 M2 using GBW specification, and using this equation we can find out the values of GM, and using the GM we can use this equation to find out the values of W by L of aspect ratio of 1 and 2. And using CC relationship, we can find out the CC and CL relationship, we can find out the values of CC to be 0.8 picofarad, and using slew rate we will find out the values of required bias current. So in this case, required bias current is 16 microampere. Now design of M3 M4. As we know, this is a common source amplifier, the half circuit part of this two-stage op-amp, and to keep the MOSFET M3 M1 in saturation, we have to follow this condition, and these are standard equations, you can follow it from any designs book. I have jotted down here from Alan and Hallberg book, writer Alan and Hallberg book, and using this equation I have found out the aspect ratio of 3 and 4 to be 14. Next, design of M5 M8. Again, by using the ICMR mean specification, we can find out the values of BD set of 5, and using BD set of 5, here it is found to be 100 millivolt. Using these values, W by L of 5 and 8 is found to be 8.42. Now designing of M6 and M7 from phase margin specification, that is 60 degree, and the relationship GM6 must be greater than or equal to 10 times of GM1. This is again derived and shown in the book Alan and Hallberg book, CMOS analog circuit design by Philip E. Allen and Douglas R. Hallberg book. From this book I have taken this relationship, and using this relationship I have found out the values of GM4, and using this relationship I have found out the values of W by L of 6 to be 128.9, and using the same current, as I6 is same as I7, this W by L of 7 is calculated and is found to be 38.48. So this is the final W by L ratio of all the MOSFETs used in two-stage op-amp, corresponding load capacitance and bias current, and common mode voltage is 1 volt, used, and WYL of 6 is further tuned to match the PDK value or support the PDK value. And so let's see how it works when it is fed to the cadence and see whether we can meet our specification or not. So let's go to the demo and see how it works. So log in to your Linux machine, go to your work folder, open in terminal, invoke virtuoso. So here this is the cadence console. Go to tools, library manager, go to file, create new library. So I have created two-stage opamp as my new library. A pop-up will come. Select attached an existing technology library. Press OK. Select TSMC65 Technology library. Press OK. Now go to library manager. Selecting on this library, go to file, new, cell view. So again a pop-up will come, give any name, opamp. So this is the schematic editor. You can now invoke the instances and call the instances to draw the circuit. So let us draw the circuit first. So we require PMOS and MOS. So first of all, let us search it for PCH PMOS. Place it. To sidewise rotate, you can click on this. Escape, press escape. Press I. Now press I again and search it for NCH for NMOS. Now place it, create the differential pair. Now create the tail MOSFET, again sidewise. Now again press I, sidewise. Now this is the MOSFET requirement is complete now. Press escape. Now wire this. All body terminal of the PMOS should be connected to the VDD. These are the input. There is the mirror. Now connect all the sources by pressing W for where. Now you can connect this to this. Now let us give the pins B in plus, B in minus. These are input pins. So B in plus is this, B in minus, R for rotate, again I base, and output pin V out. Next we need one CC, so create one CC in pin here. So this is it. Now let's create VDD pin and ground pin. VDD and ground. Now connect this body to the ground. I think all are connected now. Second save. Now using the specification, we will now configure this design. So select this, press Q. According to our calculated values, W will be 6 micro and L is 1 micro. Six micro, 1 micro. Next, select this, L is 1 micro and W is 14 micro. Select, apply to all selected, press OK. Next, these two MOSFETs are equal as per the design. W is 8.42 micro and L is 1 micro. And this is as per the tuned design final value of M6. L is 200 nano and W is 65 micro. Here press Q. L is 1 micro, W is 38.42 micro. 42 or 82, let's check, it will be checked later on. Check and save. Now let's create the symbol of this design. Create, go to create, cell view, from cell view, press OK. Now give your pin accordingly. Yes, okay. Your symbol is created. Now if you want to design the symbol of amplifier, you can design it by deleting this box. Use this where now drag this pin close to the box. Second set. Now let me check the values. So these are the final value, as we have 8.42 and 65 by 0.2 macro means 200 macro. Rest are okay. 8.42 38.48 rest are okay. Checked. Now close it. Go to tools, file manager or library manager. Click here opamp test bench to test their circuit. Now press I. Use your symbol here. Give input from analog library. PDC 1.2 volt power supply. And the input, 2 input, and one IDC is required, bias current, which is 16 micro according to our specification. One VDD terminal. One ground. Now connect using W. Press W to connect. You can use wire name B in plus, B in minus, plus minus. Similarly, name these pins as B in plus, B in minus. Okay. Now connect. Now I have connected capacitor as CC cap. 800 femto, R for rotate, and 1 for your load capacitance is 2 pico. Now create one pin as for V out. Now select the common mode voltage to be 1 volt. Maximum ICMR I have used. And in Bean plus, let's give AC magnitude 1, that is change in input voltage, that is del V in is 1 volt. Now check and save. Go to launch, ADL, let's do AC analysis. So after launching ADL, check the setup model average whether it is present or not. Yes, it is present. Go to analysis, choose AC 1 Hz to suppose 1 gigahertz, logarithmic 100 point per decade. It is just the resolution you are setting. Run it. Go to result, direct plot, AC gain and phase. V out, by click on V out first, then Bean plus. So it will show a border plot. Now we will check, split it using this. You can see here 60.36 dB gain is coming. According to our specification, we have set to 60 dB. And let me check other parameters what we can get from this graph. So if you press H horizontal marker, then 57.36 minus 3 dB, 57.36, we will get the bandwidth, that is 20.33 kilohertz, and at 0 dB we will get the GBW. So GBW is less than 30 megahertz, so it is coming 20.42 megahertz coming practically. So next, using vertical marker, you just point out the 0 dB 20 megahertz and found out the phase value minus 112.35 degree. Subtract it from 180, you will get the phase margin. So press H, minus 180. This is the phase crossover frequency, 113.10 megahertz. This point is the phase crossover frequency, and this is the gain crossover frequency. So for stability, phase crossover frequency must be greater than gain crossover frequency. So from this observation, it is found that our system is stable. So if you press H again here, you will find the phase margin between this two horizontal line. This is your phase margin. And if you press again vertical marker here in this intersecting point, and if you press again horizontal marker in the gain, you will find the gap between this H2 and H5 is the gain margin. So these are the observation from this graph we can obtain, and you can found that, and it can be found that our required specification meets with our values that we have put in the cadence, calculated values. So this is the SE analysis. Okay, this is the setup for SE analysis. You can find gain, phase using this setup. Bandwidth, GBW, gain margin, phase margin, everything can be found using this analysis and using this setup. So now let us proceed to the other analysis using SE analysis, that is CMRR analysis. How we can find the CMRR value of, or how we can plot the CMRR curve using this setup. So for that, go to this B in minus, press Q, keep X in the SE magnitude plot, SE magnitude field, press OK, check and save. Now go to ADL, right click on this, copy from cell view, 0, put 0 initially. Now as we know, CMRR is AD minus SE, that is differential gain minus common mode gain. So we will plot two gain plot. One is differential gain plot, and that is common mode gain plot. So by subtracting AD minus SE plot, we will find the final CMRR plot using equation editor or calculator. So let's run it first using parametric analysis. Go to tools, parametric analysis, select this design variable, vary it from 0 to 1 volt, and we require only two graphs, so 2. Run it from here. So it is run, simulation is completed. Go to results, direct plot, gain and phase, B out by B. So you will see two plots. Delete the phase. Now this is your AD and this is your SC. Now you subtract this from this, subtract this from this, we will get the CMRR plot. So select on this, send to calculator. Now copy this, Control C, select this, copy this, press minus, Control V. Now replace it 0 to 1. So this is your common mode gain and this is your differential mode gain. Now plot it. So you will see a blue curve is coming here. 70.48 dB is the CMRR. So we have set the CMRR greater than 60 dB, which we have found 70.48, which is maintaining our specification. So this is how we can find the CMRR using SE analysis. Close it. Now let us do some other analysis. Now let us do PSRR analysis, power supply rejection ratio. This analysis will quantify that how much noise that opamp can reject from coming from power supply. So we have to check this parameter PSRR, power supply rejection ratio. So for that we have to change the setup. So let's see how it should be done. So delete the negative terminal name, just connect it to the output, make it as unity again opamp, and keep as it is, give SC magnitude to 1 volt. as we are checking the noise from power supply itself, so we are introducing a small change in voltage in in power supply. In using this field, we can introduce this small change. So AC magnitude we have given 1 volt, apply, okay, second save. Another setup is for PSRR is we have to ground this B in plus also, but in this case, as we have set the common mode voltage to 1 volt each, so we have to give the bias voltage, just bias voltage. I have removed the AC magnitude value from this input, so I just given the only the bias voltage to keep the op amp in proper region and make it a unity gain buffer. Now I have given a small change in voltage in power supply, so check and save. Now go to launch ADL, analysis, choose AC analysis 1 to 1 gigahertz. Hundred points per decade. Now run this simulation. So, oh, some parameter value is there I have not given. That's why, so give x value to 0. Some design variable parameter is not given provided value. That's why it's shown error. Now again run it. Go to result, direct plot, AC gain in phase. Now we have to check VDD by V out. So it will give a, delete the phase plot, it will give a gain 56.97 dB. So this is the PSRR class of this op amp. Another parameter is PSRR minus, but in this case we have used ground, so there is no negative voltage given to the instead of ground, so it is not required PSRR negative, only PSRR plus will solve the purpose. So this is the PSRR analysis. Using this setup you can do PSRR and plus analysis, and for PSRR minus it is not required here, as we have used ground to the negative terminal, and you have not used any negative voltage. So this is the PSRR analysis of the op amp. Okay, so close it. Now from AC analysis we have got gain, phase and CMRR, and now it's PSRR. So using AC analysis we can get 3 distinct parameters. One is gain phase, another is CMRR, and another is PSRR. So let's move on to another analysis. So let's do DC analysis. So this is the normal setup as we have done in AC analysis. Using DC analysis we can check ICMR plot and the region of operation of MOSFET, how we can find the region of MOSFET, whether current distribution is proper or not, we can check. So for that, double click on this, new tab, press OK. So here is the schematic, this is your test bench. Now so for this we have to uncheck this AC analysis, no need. We have to set the analysis to DC, save DC operating point to check the DC operating point. Let's apply, okay. Now run it. We are now checking what are the region of operation of every MOSFET, node voltage, everything. So go to result, print DC operating points. Now go to the schematic, you can check this MOSFET. Click on the MOSFET, you will find the every parameter of MOSFET along with VTH and region of operation. This is region 2. Region 2. Similarly, if you click on this MOSFET, it is also in region 2. So in this way you can check all the device region of operation. Along with you can do annotation. So right click on this, go to annotation, click on DC operating point. So you will see that current division. We have used 16 microampere, so almost 15.7 microampere is copied flowing through this tail MOSFET. It is again divided in two parts, equally distribution is there, 7.84 micro drain current. So almost equally distributed. This is the final current, output stage. So in this way you can find all this current distribution and the BGS and BDS, VTH, every values you can obtain from this analysis using annotation. Now if you like to do setup, click on annotation, go to setup, click on TSMC. Suppose you want to see all the region of PMOS, then go to this field, if region, apply these settings to all. So you will see this is region 2, region 2, region 2, all the MOSFETs are in region 2. Similarly, if you want to see the regions of PMOS, go to TSMC NCH, click on this field, region, okay. So you can see all the region of MOSFET, that is NMOS, are shown here, region below. So in this way you can see all the regions, current distributions, node voltages using DC analysis. So now close it. Now we will check ICMR plot or ICMR ranges. For running ICMR, we will again delete this pin name and loop back to the output. Check and save. Now click on this and go to the ADL, click on DC, right click on it, edit, select component parameter, select component. We are now varying the input DC parameter, zero to maximum voltage. Press apply and we are going to plot input voltage versus the drain current of M5, and if you want to see the drain current of any one of the MOSFET, you can also plot the ideal. So M5 source is not required, gate is not required, body is not required. So I am plotting two drain currents and along with input voltages. So run the simulation. So here you can see the drain current of this tail MOSFET. You can see the ranges, as we have chosen 0.6 is the minimum ICMR and 1 volt is the maximum. So in this region you can see the MOSFET is going to be saturation. So according to our specification, the results are coming within our ranges. So this is what ICMR analysis. Oh, M5 drain current is not plotted. So again run it. You will find the two drain currents. Yes. So you can delete the P in plus, or you can keep it. You can see here, this is your M4, which is a less current. You can see 7.55 or 7.82 like that. So if you increase the common mode voltage, you can increase the current little bit. Due to the short channel effect of this MOSFET, it is not going to be constant after saturation. If you use long channel MOSFET technology, this line will be almost straight line. So we have selected this region 0.6 to 1 volt is our ICMR mean and max range. So in this way you can run the ICMR plot. You can delete this B in plus and check these two currents. One is the drain current, total tail current, which is most important. If this MOSFET is in saturation, all other MOSFET will be in saturation. So in this way you can check the ICMR plot. You can also check the static DC power consumption using this technique. Go to results print, DC operating point, click on the power supply. So it will show the static current, or you can say the whole total current power consumption of opamp, static power consumption of opamp 131 microwatt. So using DC analysis you can check ICMR, DC operating points and static power, and also you can check offset voltage. So using of this setup only you can also check DC output offset voltage, how much it is coming. So let's modify this and plot the output voltage. If you select the wire, it will give voltage. If you select the node, it will give the current. So I am plotting the output voltage. Run it. So according to ideal opamp, there should be a zero output voltage whenever there is no change in input. So we will find how much value it coming at input when input is in 0. So let us click on this, send it to calculator, function, go to value, interpolate at 0. So we are interpolating at 0 value of input voltage how much output is coming. Press OK. Now calculate. 1.42 millivolt is coming. This is your offset voltage, 1.42 milli. So using DC analysis, we can check these sorts of analysis. That is, first DC operating point can be checked. Next, your ICMR ranges can be verified, and static power. These things can be checked using operating regions of MOSFET, node voltages. This type of things can be checked using DC analysis. Now let's do transient analysis. So using transient analysis, we are going to find first slew rate of this op-amp, second our output voltage swing, and the third is our dynamic power or transient power. So these three analysis or three parameter will be found using this analysis. So let's do the setup. For transient analysis or for doing slew rate analysis, we have to remove this BDC, and or you can directly click on this, press Q and change here B pulse. Okay, so keep as it is. Here you can give 0 to 1 volt, period say 500 nano. Don't give price time, full time. Pulse width half of this 250 nano. Press OK. Now go to ADL, go to analysis, choose transient, say 5 micro. Use conservative mode of operation for high resolution output. This is medium resolution output. It will collect moderate samples of data in every instant of time, and this is leverage less instance of low resolution simulation. For complex circuit, you can use liberal mode. So let's run this. We have to check and save. If you change anything in your circuit, press check and save and then run the simulation. So this is the output. Now click on this, send to calculator. There is a function called slew rate. Click on slew rate. Now minimize this, check the minimum value 298.57 millivolt, and this is the 999.89. so feed it in the function. Initial value is 298 milli and final value is 999 milli, and from this it will extract 10% and 90% ratio. That is, from low initial input it will collect 10% of initial, and from final 90% of final value, and then calculate the slew rate. Press OK. Now press calculate. So this is 18.13 mega, means 18.13 volt per microsecond is the slew rate. So our target is almost 20 volt per microsecond. So it is almost close to the expected value. So this is the slew rate. So in this way we can check the slew rate of the op-amp. Now you can also double click on this, copy this equation and right click on this, edit, slew rate, get expression or paste here. You can also press get expression from calculator itself, or you can copy paste here. Press OK. Now if you run, you will directly find the value here, 18.13 mega. So this is the slew rate analysis of two-stage op-amp. You can use this setup arrangement to find the slew rate of op-amp and do transient analysis. So now let's check other parameters, that is dynamic power and output swing. So for that, now this is a setup for checking the output swing of the op-amp. Here I have given 1 kilowatt frequency on 1 millivolt. You can also reduce depending upon the gain. So as it says around 60 dB, the 1000 time it will come. So you can also reduce the input amplitude. Otherwise, it will give saturated output and the output saturated output as the output. 500 micro. Oh, check and save. You have to check and save it. So this is the output. Some distortion is there. So you can change the common mode voltage, arrange the common mode voltage to meet the output waveform. Now, so if you check the swing, you will find that around 1.11 is the maximum voltage, and minimum is 278.54 milli. So subtract this V max minus V min, you will get the output swing, or you can send it to the calculator function, go to Y max Y min. Click on Y max, copy it, subtract, change Y min, plot. So you will find the output swing 835.0 millivolt is the output swing. So this is it. Now you can go to the output, press save all to save all the power signals for getting transient power. Now again run it. Close it, go to result, or you can go to tools, result browser, expand this, click on run. Here PWR is there. So this is the power plot. So you can click on this, send to calculator function, click on average. So this is the average 117.4 micro is the dynamic power. 117.4 microwatt is the dynamic power. So in this way we can check dynamic power, or you can check from this. You go to results, direct plot, main form. So here you can see power, select total power, plot. It will give same output. So in two way you can check the power of the op-amp, that is dynamic power of the op-amp. Here you can see into calculator, take average, here you can see 117.4 micro is the average power. But in case of DC static power, we are getting a power of 132 microwatt. This is due to the external DC bias circuit. We have not generated this, also taking some power. So all total power is shown in the power supply. That is, if you do DC analysis and print the DC operating point of power supply, you will find (130 microwatt). So this difference is due to the power consumption of I bias is not considered in the dynamic power in this case. So this is it, the transient analysis. Another analysis is there which is called noise analysis. So for that, go to analysis, choose, click on noise, frequency 1 Hz to 1 gigahertz, 1 gigahertz, select logarithmic 100 point, select on output voltage, select the positive node, select the negative output node, that is the ground, input noise source, select on the input signal, press apply, OK. Now run this. Okay, now go to results, direct plot, main form. So click on input noise. This is the unit, plot it. So this is the noise plot. In this part, this is the flicker noise. This area is the flicker noise part, and these are thermal noise plot. So this is the noise plot. At 1 Hz, it is around 4.7 microvolt. So at 1 kilohertz, around 152.6 nanovolt. So this is in this way you can find the spot noise, in that what frequency how much noise voltage is coming, RMS value. Now you can check input referred noise using, go to this result, noise summary. Here you check the indicated. This indicated noise is the noise in your required bandwidth. So our bandwidth is 1 Hz to around 20 kilohertz. Bold, unit should be in bold. Include all types of noise sources. Press OK. So this is 15.7 microvolt is the input referred noise, you can see here. And from this list, it is showing that in which MOSFET is contributing how much noise percentage. So top 3 noise contributing MOSFETs are listed here. You can check those MOSFET and do the further tuning to reduce the noise. So this is it, noise analysis. So in this way you can do all the analysis of opamp. By watching this video, I have summarized all the important analysis in this video. So hope if you find some valuable information in this video, please keep watching and keep supporting me so that I can make lots of videos for you which may helpful for you. So Thank you all. Please share and subscribe my videos.